We're going to introduce the logic of statistical hypothesis inference testing. And we're going to introduce it by reference to a very popular film called Casablanca. So the object of this particular presentation is that we end up being able to interpret the results of a randomization test. Hopefully the coursework is driving us to engage a little bit with doing a randomization test. So what we're going to do is to pick up some of the key jargon around hypothesis testing, and the first bit of jargon that we've got to think about is this number here, 0.05. That's what's called the default size for a statistical test. Usually we're interested in finding out whether a particular quantity called a p-value is less than that number. We'll explain what all that's about as we... So, I find the logic of statistical hypothesis inference testing rather baffling, and it's interesting in this real great movie classic Casablanca. The protagonists we're interested in, this is Ingrid Bergman, who plays a character called Ilse. This is Humphrey Bogart, who plays a character called Rick, and this is in the story Ilse's husband. And basically at some point in the past, Rick and Ilse have been an item, and she's now moved on and is married. And one of the classic scenes is that she appears in Rick's bar, and the famous quote, "Of all the gin joints in all the world, she has to walk into mine." And we're going to unpick the logic behind that particular stuff. If you want to watch the clip that it comes from, there's a YouTube link given with the lecture slides, but the salient points here are that Ilse is now married to Victor, but she appears in Rick's diner. And from that quote, it's as if Rick is trying to work out whether she's appeared as a pure act of randomness, or whether he believes that she's there for specifically to see him. So, here is an example of Rick's reasoning. And what we do is we assume a hypothesis, which we can call a null hypothesis, that Ilse is no longer interested in Rick. And if that were true, the probability that Ilse walks into his bar would be 1, because she's walked into his bar, divided by all the gin joints in all the towns in all the world. Now, I don't know what number that is for certain. It's a massive number, therefore this is a very, very, very low probability. So, given the observation and the probability of getting an observation like that if the null hypothesis is true, Rick rejects the initial assumption, what we've called our null hypothesis, and concludes that perhaps Ilse is specifically there for him. Set this out slightly more formally. We have a null hypothesis. Ilse is not interested in Rick. We have an alternative hypothesis. Ilse is romantically interested in Rick. And we have the probability of obtaining the data we got if the null hypothesis were true. It's 1 divided by a very big number. And because this probability is lower than our conventional 0.05, we reject the null hypothesis. And we make the conclusion that Ilse is particularly interested in Rick. So, the key point to note, whether we like it or not, this thing called a p-value that pops up is something to do with probability of getting data, or even more extreme data, in a virtual world where the null hypothesis is true. It's all about the probability of getting data given the null hypothesis. So it tells us nothing about the probability that a hypothesis is true or false. It has nothing whatsoever to do with that. All we can do with the p-value is to make a decision, and the decision rule is decided in advance. If we've picked a size of 0.05 and the p-value is less than 0.05, we are entitled to reject the null hypothesis. There's some interesting consequences of this decision rule. If we were in a world where the null hypothesis were true and we carried out this kind of procedure, 5% of the time we carried out the procedure, we would reject the null hypothesis and we would be declaring false positive results. We would be telling people our treatment was effective even though it wasn't. So one of the key ideas here is scientific reproducibility demands that we replicate studies. Another interesting and rather subtle point, we set up the illustration with this as our null hypothesis. Ilse is not interested, and we gave the alternative that she was romantically interested. And as I note here, they're not logically opposite. It's possible Ilse left a lottery ticket in Rick's flat and is only seeking him out because she wants to go and make a claim. So the point here is you can reject the null hypothesis for reasons other than the alternative being true. So we could reject the null hypothesis that Ilse is not interested in Rick because she's interested in him, which doesn't have to be romantically interested in him. Another thing to watch out for, particularly true with massive data sets, it's possible we reject null hypotheses just because of a blip of the data, just a feature of particularly large data sets. It's not clear how well the sampling theory that underlies this works. The second thing, if we carry out lots of hypothesis tests, some are going to be false positives. We sort of said that already. If the null hypothesis is true, 5% of the time we're going to declare a result as statistically significant. And finally, and this is really important, even if we claim a result is statistically significant, we might find that the effect size is so small as to be completely irrelevant. So more specifically, we've set ourselves up on this course to do a two-group comparison. So we have a very specific null hypothesis. We're saying that mu1 equals mu2. mu1 and mu2 are the parameters of the mathematical model that describes the data generating mechanism. They're unknowable quantities. We can write the null hypothesis slightly more mathematically, that if they're the same, then if I subtracted mu2 from mu1, I would get 0. So what we're going to do is conduct a controlled experiment where we randomly allocate subjects to either the treatment group 1 or the control group 2. And if the null hypothesis is true, the difference between the sample means should be 0 plus or minus something we call sampling error. And just notice the little pedanticism. We're not using error here to mean a mistake. We're just using error to mean all the randomness that can enter any natural system. And the question we have is that sample mean 1 minus sample mean 2 will never be exactly 0. So how do we decide whether the difference is so far from 0 that we don't believe it's sampling error and we're allowed to reject the null hypothesis? And what's interesting, in the context of a designed experiment, if the null hypothesis is true, we're saying that the group labels, treatment and control, are arbitrary. The only reason we got the sample mean we got from the treatment group was because we randomly allocated those subjects to that group. If we'd randomly allocated some subjects to a different group, that data would have ended up in the other group and contributed to the sample mean of the other group. The idea behind a randomization test is that we can shuffle the data very, very, very easily, and the asterisk notation here is to denote the idea that I have shuffled the data set between two groups of the same size arbitrarily. And what I get is a plausible arrangement of what the data could have looked like if the null hypothesis were true. And of course I can do this thousands of times and create thousands of virtual worlds that tell me those data could have looked like this. If the null hypothesis were true, you could have got this big a difference between sample means. Therefore, all I need to do to decide whether my null hypothesis is plausible is count how many times I get a simulated difference in data means that is bigger than the absolute positive difference or the absolute negative difference between the observed. So what I'm saying is, if I get a difference of 3.65, I'm looking to see how many are bigger than plus 3.65 or smaller than minus 3.65. If I happen to get minus 3.65, I'm still looking to see whether they are bigger than plus 3.65 and smaller than minus 3.65. And the number of simulations divided by the total number of simulations gives me an estimate of the probability of getting data as extreme or more extreme than the data we actually saw if the null hypothesis were true. In other words, this is our p-value. I have an estimate from a computer simulation of the probability of getting as extreme or more extreme differences between group means if the null hypothesis were true. And the convention goes, if this probability is less than 0.05, I reject the null hypothesis. Notice this is just a dumb rule. I decided what the cutoff number was, 0.05, before I did anything else. I computed this p-value, but all I do with that p-value is plug it into a decision rule. And if the p-value is less than 0.05, I can say things like the results are statistically significant. And again, pedants alert, when I say statistically significant, I'm just saying it is signed. Very precise meaning that's out of line with common English usage. I'm saying the difference between means is bigger than can be explained by sampling error alone. It may not be a practically significant difference. So, a couple of comments on the tutorial. Basically, you did a fantastic job getting the macros working, so you should now know how to do some summaries. So with the real data, we're looking for a mean, standard deviation, we're perhaps looking for a 5-number summary, and we're looking for some visual summaries such as a histogram for each group. And just note, you have 5 small changes to make to your macro to make it work with the full data set.